Then 8.8 will just mention the the main concept. Some of these are details, analysis, especially evaluating those integral, not be that. So basically, the concept is about this Q factor. So to define what we call the quality factor for resonators, the Q is defined as you have that so you have a resonator, whatever the geometry. So you have a total energy inside. These are the total field energy, the electric and magnetic field energy inside. And then assuming it's not exactly perfect, the conductance is not infinity, so it's large, but that, it may not be large, large is small, finite conductivity, so we have energy loss. So we have so if you start with a mole with U, then it will change in time. So you have du dt energy loss. Usually, of course, this is energy loss is negative. So you need to define it with a negative sign. So you define this as Q is defined as U divided by the energy loss in a typical time. Is not exactly the periods of du dt times the typical time scale, which is 1 over the resonant frequency, or omega sub 0. And to make this positive, we add a negative sign. Put it the other way here. Okay, so that's the definition. It means that Q is large if the dissipation is small. Usually, you have a resonator with very small dissipation, then Q value would be larger, vice versa. All right. Assuming Q is a constant, you can solve du dt equals to minus omega 0 over Q times U. Just put this to here, put this to the other side. And obviously the solution, you know how to solve this differential equation, right? Very simple. So use whatever the initial energy and the decay in minus omega 0 over Q times. Right, do that kind of trivial. And this is energy. So energy usually is proportional to or some integral of E squared. So it's a square term. So the field quantity actually decay with instead of this exponential function is exponential function. Square root of that, so you have a factor of 1/2 in the decay rate. The ET will be the typical field inside the resonator. You can define it as E0 e to the minus 2 omega sub c into 2 Q times T. And you measure it, usually we measure the spectrum, or maybe take a Fourier transform of that and look at the spectral width. So this is resonator, so you have some resonant frequency. At some omega sub 0, you measure the Fourier transform of it, the absolute value square Fourier transform. So you have a certain profile. The center at this one, if it will show that when if Q is good, large, then the width of this spectral line will be small. Okay, so we'll see that right away because we can take the Fourier transform of this. The Fourier transform is given by you can do the convenient convention, either the symmetric convention or whatever convention. Doesn't matter. What we just consider the shape as a matter vector. So basically, integrate minus infinity. But usually you integrate minus infinity, but in this case, obviously this one starts from 0. Otherwise, if t is negative, it's growing negative term, it doesn't make sense. So we usually start with t equals 0, so we have a step function t. Right. So when you do the integration, you can change this to integrate from 0 to infinity. And you have e sub 0, e to the minus omega sub 0 to q e, and then plus I omega t. That's how you do the integration. Yeah. I think Jackson also shift this to a little bit. If you add the finite conductivity, the frequency also shift. But for us, it doesn't matter whether you shift it or not because we're looking at the width only, not exactly the value. So this integration is trivial. So you can just write it out. You have e sub 0. This is just exponential function, right? So you divided by the argument minus omega sub 0 tq plus I omega, and write down the exponential function again. Evaluate at 0 and infinity, right? And at infinity, obviously this is 0 because of this factor, assuming omega sub 0 and q are real, so at infinity and with the negative sign, this is 0. The whole thing is 0, so only contribution is from 0, t equals 0, and it's in the negative limit. So 0, 0, 0, minus that. All right, so that is straightforward. Now the spectral wave, you need this compact magnitude square. Well, we only consider this omega sub 0. Usually you have a minus omega sub 0, and then you can actually, most people just fold it to positive values. So usually these Fourier transform are symmetric. You have a minus omegas. When you do the Fourier transform, you have a minus omega, but you can consider just the real positive omega sub 0. It's just the same thing. So absolute value square is 0 square. Absolutely, it can be compact. So, compact magnitude square of the denominator is also straightforward. It's just the square of the real part plus the square of the square of the imaginary part. The square. Oh, I missed a term. Well, that's why I'm. So you have a. I have this. This usually. This is oscillating. So you have a minus I in oscillating. Minus I in the oscillating. That doesn't matter. This changing. Minus that more like it. All right. So now you can look at the shape of this one. So, obviously, this function will be we have a maximum at omega equal to 0 because both are square term. This is like a constant. So you get rid of this term will make it maximum. So the maximum is omega over omega sub 0, not considering a shift in the frequency. And whatever the maximum value, this is whatever the maximum value is, this value, I should say, this value is E0 square 2 pi, and just this term, so you have okay, so that's fine. And the one characterization of a spectral line is how narrow or how wide this peak is. Usually, you can look at say if you have at the value half of its maximum value, you can measure this width. This width is we define this width as down, right? This is so-called whatever they call. This is half maximum, full width of half maximum. Right? So this gamma, right? And assuming that this spectral line is symmetric, so it means this omega minus omega sub 0 becomes gamma over 2 because this is symmetric. So at the location, then either this point or this point, this is omega sub 0 plus gamma over 2 or minus gamma over 2. So this difference is gamma over 2, and then they take the square of that. And this will make this the line, the intensity of the line at half. So it means this term must equals to this term. And you compare the form of that, so this means delta is equals to omega of C over P. Okay, so that straightforward. All right, so in a sense, so then we can say that this is UC minus omega sub C over Q is this gamma. This gamma is just the full width of half maximum. Okay, so that's all the concept, and so the main concept is when you have a good resonator with small high conductivity, small dissipation, then Q is large. When Q is large, then the line width will be small, given by this dependency. The gamma is depends on 1 over Q. Okay, so that those are the basic idea, basic concept. All right. So you can experimentally measure the resonator, how good the resonator by just measuring the spectral line, the width of the spectral line, and then you can actually get the Q. We usually calculate Q would be more complicated, but measuring experimentally a spectral lines is easier. Okay, so that is this conceptual consideration. Then the calculation of Q from what we did before, considering the finite conductivity and use the boundary integral that we talked about in 8.1. I mean, in the waveguide, we did that before also. So that would involve calculating U with the integrating E and B energy inside, which we did that for waveguide also. So the final result is 8.92. So it's, the only difference is that now we integrate over the whole volume. So integrate along this direction C from 0 to D. the electric field, magnetic fields have sine and cosine dependency on the c direction, but that integral is straightforward, easy to integrate. And the rest of the integration is similar to the waveguide. And the power laws also, power laws, we in waveguide, we already consider you integrate the size surface for unit length. Here, you don't integrate it over unit length, you integrate over the whole length. See what we do? That's fine, it's just the same. And then you integrate also the end surface. So you have two extra terms from the end surface for the power loss, which you can also write it out. And the formula for that is 8.93, although you substitute the exact wave, the exact form of the wave depends on TMO, TMO, that those integration complicated. Right, so you can estimate, like what Jackson did, 8.94 and 95, do some estimation, but the ultimately is still some estimations. Full integration, exact integration is too complicated to do. Most likely you need to do it numerically. Okay, but there's one thing that we can finally talk about. It's just dependency, general dependency to Q. So Q is a dimensionless number because we defined it in a way is dimensionless, and ultimately it depends on the ratio between the energy content and then the energy loss. The energy content is obviously proportional to the volume. Whatever you have a larger volume, you have more energy. So if you estimate it, what is proportional to the volume of the resonator. And then now the power loss, and we already mentioned that the power loss is just integrating all the surface integral of the field on the surface. And we have formula for that, but the estimation is that it depends, it's proportional to the area. Larger area, you have a larger the surface integral, so it's inversely proportional to the area. And now we're looking for a dimensionless number that will give you Q. So this is volume, this is area. So we need another length number of the dimensional length of the problem to make it dimensionless. And in the case for finite sigma, and especially in the limit of large sigma, it's near perfect conductance, but then it's not exactly infinity. So it's, and we talk about when in that case, all the surfaces, you have some loss into the conductor. So you have some field that leak into the conductor. It's the delta, right? And that is so-called the spin depth, and this is this delta that gives you the dissipation, because this delta depends on the conductivity also, right? And delta, the spin depth is a dimension of length, so it's quite natural that delta should go into here. So to make it the ratio V divided by A delta, because it's if delta is small in the ideal case, this will recover the ideal situation where Q is infinity. When delta is large, then this is the sigma is small and the resonator is not that good, so Q is small. And you can look up the delta. Dependence of the delta, I see is listed already in again in this few sections before. So I think maybe in section 1 or 2. Delta is here 8.8. 2 over mu, whatever the suspectability is, mu over omega c. Right? So we have we have the frequency inside the resonant frequency, and then the conductivity. So large conductivity means more delta means large Q. Okay. And of course, this is just an estimation. Usually we need to multiply by some geometrical factor, some other constant. Okay, so that's the estimation. Just did a little bit more and estimate for some node. But don't want to go into that much detail, but just have some kind of a qualitative. It's okay. So that roughly the dependency. And so that's this 8.8. Any question? Is that okay? 8.8.